In this video, we're going to take a closer look at the set of all rational numbers x such that x squared is less than 2. I know that I've already talked about it in a previous video, but then I was asking you to believe me. Now we are in a position of showing that indeed the supremum of this set is the square root of 2 and that it is impossible to find the supremum of the set in the rational numbers. But before we do that, we need to show another theorem, and it's one that says that the rational numbers are dense in the real numbers. But what does it mean? Well, it means that if I pick any two real numbers x and y, such that x is less than y, there exists a rational number r such that r is between x and y. So what this is telling me is that no matter which two real numbers I pick, no matter how close they are to each other, I can always find a rational number that is in between them. I'm not going to give the proof, but I'm going to give you an idea. And this is the idea. Well, first I'm going to restrict myself to the case that x and y are positive because it's a lot easier to see it. So I'm going to just draw it for both x and y positive. Here we have them, x and y. And well, I don't know, maybe they're very, very close to each other. But you see, if I multiply both of them by some very large number, n, then the distance of n between nx and ny is going to be quite large. So what I'm going to do is that I'm going to find an n large enough such that the distance between nx and ny is bigger than 1. And why is this? Well, if I know that nx and ny are more than 1 unit apart, then I know that in between them I have to have an integer number. Right? Try to think about that. Okay, so if you have convinced yourself that that is the case, great, let's continue. If not, then pause the video and try to think about why, if the distance between nx and ny is bigger than 1, then we know that there is an integer in between them. Okay, so here I have my integer m in between them. And if you see, now what happens is that I have that m is between nx and ny. Well, but I have to conclude something about x and y. So if I divide now everything by n, what happens? Well, now I bring in between x and y, well, m over n, right? Because we have that nx is less than m, which is less than ny. So dividing everything by m, we end up with x is less than m over n, which is less than y. Oh, perfect. M was a natural number, n was a natural number, so m over n is a rational number. So we managed to construct a rational number in between x and y. And that is precisely what we wanted to show. And I will leave for you as an exercise to complete the details of this proof. Now that we have this theorem in our toolbox, let's see how we can use it to our advantage. Well, again, remember, our goal is to show that the supremum of the set of rational numbers x, such that x squared is less than 2, is the square root of 2. Now, notice that if x squared is less than 2, well, that means that x is less than the square root of 2. And, well, that tells me then that the square root of 2 is an upper bound for this set S. Good. First part done. Now, we need to show that the square root of 2 is the smallest upper bound. Okay, how do we do that? Well, the usual trick, we're going to take a number, an arbitrary number, less than the square root of 2, and we're going to show that that number cannot be an upper bound. Okay, so here we're going to split it into cases to make our life a bit easier. If h is less than or equal to 0, then h cannot be an upper bound because you see, 1 is a rational number, and 1 squared is equal to 1, which is less than 2. So anything less than 1 actually cannot be an upper bound. What happens now if h is between 0 and the square root of 2? if h is between 0 and square root of 2, we know that we can find a rational number that is between h and the square root of 2. So let's call this rational number r. So we have that there exists r in the rational numbers such that r is between h and the square root of 2. And this is because we just said that the rational numbers are dense in the set of the real numbers. But look at this. We found a rational number r that is bigger than h, but when I square r, that is going to be less than 2. Well, then that shows that h cannot be an upper bound for s. So any number h less than square root of 2 is not an upper bound. That means that the supremum is indeed equal to square root of 2. Very good. So now we know that this is true. We have a proper proof of this fact. Now let's see, how can we see that the set of the rational numbers x, such that x squared is less than 2, does not have a least upper bound in Q, in the set of rational numbers? Well, in the previous example, we saw that any number alpha less than the square root of 2 is not an upper bound for the set. So in particular, we cannot find a rational upper bound that is less than the square root of 2. So that is out of the game. Well, so if Q is a rational number that is an upper bound for this set, then, well, Q has to be greater than the square root of 2. It cannot be the square root of 2 because that is not rational, and it cannot be less than the square root of 2 because we already saw that any number less than the square root of 2 cannot be an upper bound. Okay, so we have that Q is greater than the square root of 2. But since the rational numbers are dense in the set of the real numbers, we can find a rational number r such that r is in between the square root of 2 and my upper bound Q. Oh, okay. But then what we managed to do is we managed to find another upper bound that is rational and that is smaller than the upper bound that we already had. But what this is showing is that no matter which upper bound that I pick, Q, that is a rational number. So if I pick a rational number Q and that number Q is an upper bound, I can always find another rational number R that is less than Q. Okay, but if that happens, that means that it is impossible to find the smallest upper bound in Q. Therefore, the set S has no least upper bound in the set of rational numbers. And that completes the proof of really how different the rational numbers and the real numbers are. So that the completeness axiom is giving us that fact that no matter which set we have, if we know that my set is not empty and is bounded above, immediately we have a supremum in the set of the real numbers. But that is not the case when we restrict ourselves only to the set of the rational numbers. So the rational numbers have plenty of holes where those suprema should be. So that is something to keep in mind. The completeness axiom, what it's telling us is that it captures our intuition of the fact that the real line doesn't have any holes in it.